Welcome to Kafka Summit 2021 APAC. I'm Tim Berglund with Confluent, and I'm so happy that we have an event in the Asia-Pacific region this year. As you see, we're still online. Of course, there are a lot of good things about that. That makes travel easy and inexpensive. It makes it possible for lots and lots of people to be here. But as you know by now, with our online Kafka Summit events, there is a live component. Speakers are present for Q&A, there's people to interact with, and this interaction is all happening in relatively friendly time zones. And I'm just really delighted to be in this region for the first time this year. We've got a day's worth of amazing sessions and lightning talks to offer you, all of which have been curated by the Kafka Summit Program Committee. And as always, I want to acknowledge that this just wouldn't happen without the help and collaboration and support of these colleagues of mine. I'm so grateful for their participation and their tireless rating. We're doing 3 summits this year. Their tireless rating of literally hundreds of proposals. There's so much good content that this community creates. It's not easy to sift through it. These folks do. And that helps us offer you the best program we possibly can. So huge round of applause to the Summit Program Committee. Before we get started with that, we've got a keynote. Jun Rao is going to be talking to us. Now, Jun is, as you may know, the co-creator of Apache Kafka and one of the co-founders of Confluent. Now, if you wanted to know what had been going on with Kafka as a project and as a technology ecosystem, and you wanted to know what was going to happen with Kafka as a project and a technology ecosystem, Jun might be the guy that you'd ask. In his keynote today, he's going to talk a little bit about the history of Kafka, how it's grown a data integration framework and stream processing features on top of its core distributed log functionality, and where it's going to go from here, becoming a truly cloud-native service in the form of things like Confluent Cloud, with features like infinite storage, multi-region capability, and all kinds of really necessary cloud-native forward-looking features like that. It really is nice to be able to put all this history in one place. And coming from a guy who's been there the whole time with Kafka, his thoughts about where data in motion is taking us next are thoughts that we should probably take the time to learn. So, Jun, the stage is yours.
Good morning, good evening, good afternoon, everyone. Welcome to Kafka Summit 2021 for APAC. This is actually the very first time we have had Kafka Summit in the APAC area. So welcome to all the participants from Asian Pacific. Today, what I want to do is talk about how Apache Kafka has helped create this new category of infrastructure, which we call data in motion, and how that fits into a cloud-first world. To get us started, if you are new to Kafka, this is actually one of the most popular open source projects out there. It's used widely by hundreds of thousands of organizations across the globe, across industry, including some of the largest enterprises around the world. And APAC in particular is the area where I see a lot of adoption of this technology. And if you look at some of the usage of this technology, the volume of the usage is pretty impressive. So how did that get started? Most of you probably know that the technology of Apache Kafka originally was started at LinkedIn. I was fortunate to be at LinkedIn when LinkedIn had its fastest growth. In a short period of 4 years, LinkedIn's business grew by a factor of 10. If you look inside into what really powered that fast growth of LinkedIn, it's all about LinkedIn's ability to leverage its data. Now today, a lot of companies talk about being digital first, being data-driven. But what's unique about LinkedIn is it had 2 significant realizations that allowed it to have this deeper level of leverage of this data. The first realization LinkedIn had is leveraging data in motion is a much effective way than leveraging data at rest. What do I mean by that? Well, traditionally, most of the places leverage data at rest. So when something interesting happens in the world, it just stores that in the system. After that, typically nothing happens immediately. So you have to wait until some later, typically through some batch processes, for those digitized information to be leveraged. So what LinkedIn realized is that's actually not the best way or the deepest way of leveraging the data. A better way to leverage data is instead of storing the data first and worry about what you want to do with the data later, you first define what you want to do with the data. Then when interesting events happens, it will just trigger the predefined actions. So this actually is a deeper way of leveraging the data. Now, what does this benefit LinkedIn? Well, let me just show you a few examples. Over time, a lot of the services LinkedIn has defined are all moved from data at rest to data in motion. So services like email, recommendation engine, search engine, they are all defined such that they will be constantly listening to new interesting events, such as job changes. Then when such an event occurs, it will automatically trigger the actions those services have previously defined to reflect the states in those services. Now, what's the result of that? The result is all those services are becoming much more engaging with the user, because when the user try to use those services have much fresher and much relevant information to provide to the user. So this is the first realization I want to share with you, which is leveraging data in motion is a much deeper way of leveraging the data than leveraging data at rest. The second realization LinkedIn had is the need to leverage all digitized information within LinkedIn. Now, what are all the digitized information LinkedIn has? Initially, LinkedIn mostly focused on what we call those transactional type of data. In the case of LinkedIn, these are your educational history, your job history, and your connections to other LinkedIn members. But what LinkedIn realized is over time, there's a lot of more non-transactional type of digitized information. For example, if you click on a link, you type in some keywords, those are not transactional per se, but they are as important as those transactional events in terms of deriving new insights. So if you want to be a digitized information, you need to focus not only just on those 1% or 0.1% of those transactional type of data, you need actually to focus on all those non-transactional type of information as well. So this is the second realization LinkedIn had, the need to leverage all digitized information. With these two realizations, when LinkedIn looked at all the existing infrastructures that it can use, it just surprisingly realized that most of the existing infrastructure systems are actually a mismatch for both these realizations. Well, there are two common types of infrastructure people were using at that time. The first type is databases. Well, if you look at the databases are really mostly designed for data at rest. They are not really designed for triggering actions when interesting things are happening in the world. The second common type of infrastructure people have been using are messaging systems. While the messaging systems are truly designed for data in motion, but they are really designed for flowing through those transactional type of data. So if you try to flow 100 or 1,000 times more data on this platform, then a lot of those systems start to break. This is actually when LinkedIn realized that none of those existing infrastructures fits their need. And that's when it started looking into building something of their own. So that's how Kafka was developed. When we built Apache Kafka originally, our goal is to really build a new category of data infrastructure that can handle data in motion at scale. We started with the storage component of this system, and we later added the integration layer to integrate with other parts of the ecosystem, and then we added a processing capability for people to build those event-driven applications easily. When we started with storage, we really did two things. The first thing we did is to introduce a new concept called commit log into our system, which is a first-class representation for real-time data. This allows data to be stored and delivered in real time. The second thing we did is really to design Kafka as a distributed system from ground up. In a typical Kafka cluster, you will run a cluster of those brokers, and then those commit logs will be distributed evenly among those brokers. Now together, the system can use those computing resources among all those brokers in aggregate. Over time, if your business grows and you need to add more capacity, you can just easily add more of those brokers. This is actually a pretty effective way of scaling the data. The second thing we did is to add this integration layer. If you are a typical enterprise with a little bit of history, often you will see that you have lots of data stores that are accumulating data. This can be some of the databases, can be some of the old messaging systems. To really leverage this data in motion platform, the first thing you need to do is to extract data from all those existing systems out, and then have those data published into Kafka. So what we did is to introduce this connect framework, which allow people to add those individual connectors for all those common data sources and the data sinks. Now, if you're enterprise, you want to integrate your existing system with Kafka, you typically don't have to write any code. You can just download one of those existing connectors. In Confluent, over time, we have accumulated more than 120 of those different popular connectors. Last but not least, we added the processing capability in this platform. Over time, there have been lots of those event-driven applications built on top of Kafka. And if you look inside what those applications are doing, they have some very common patterns, because a lot of those applications want to transform the data from one format to another. They may also want to do a little bit filtering, projection. Sometimes they want to do a little bit data enrichment, and occasionally they also want to do some window-based aggregation. So what we did to facilitate the building of those applications is to add a couple of processing libraries. The first thing we added is a Java library called Kafka Stream. This provides a few higher level abstractions that allows the application to specify those common patterns such as filtering, aggregation in a bit simpler syntax. At Confluent, we added another library called KSQLDB. This is a library that offers a similar processing capability, but at a more decorative level. It's using a syntax very similar to the traditional SQL language. So now, even if you are not a Java developer, by using this KSQLDB library, you can potentially write those event-driven applications using a more decorative syntax. With all those development, we now have a more complete platform for this data in motion system. At the heart, we have our scalable storage can really store that increasing amount of digitalized information in real time at scale. Using all those connectors we have built, we can integrate Kafka with all those popular data sources and data sinks. With the stream processing library we built through KSQLDB and Kafka Stream, we allow those applications to be built in an event-driven way much easier. Since the invention of Kafka, many other similar technologies have been introduced to address this data in motion space. But the adoption of Kafka continues to be strong, and Kafka is actually now becoming the de facto standard for the data in motion platform. So what's the reason behind that? For me, there are mainly two reasons. The first reason is our view. Over time, we have built a really strong Apache Kafka community. We have thousands of those contributors. We have hundreds of those meetups. We have lots of forum for people to ask and answer questions to share their experiences. So thank you for all the members in the Apache Kafka community. The second reason, which is also important, is continued innovation. Since we invented Kafka initially, we have continued innovation in this platform. So we are the first one to introduce a concept called compacted topic, which allows applications to retain the data not only by time, but also by keys. Since we introduced the stream processing capability, we added exactly once processing capability that allows each of those events to be processed once and only once, which is important for certain applications that really cares about semantics. We are now undergoing through a big effort of removing the Zookeeper dependency. By removing Zookeeper and then having a built-in consensus service, we not only simplify the deployment of Kafka, but we can also scale the amount of metadata, those topic partitions or the logs, by a factor of at least 10. So what's coming next? For Kafka and this data in motion platform to be successful, we need to continue this innovation. So what's the next wave of innovation? To me, I think the next wave of innovation is going to come from the cloud. Well, for us, we had first-hand experience in this. When we started Confluent to build this data in motion platform for enterprises based on Apache Kafka, we started with the traditional software offering. we'll add some additional software for Apache Kafka, and then we'll give this software to our users. Our users has to install the software and then operate the software. But started 4 years ago, we started offering Confluent Cloud, which is a hosted service for Apache Kafka, and is available in all the major 3 public clouds. So why did we do that? Well, the main reason is we believe this is actually a much better way of delivering the software in the future. Everyone who has run Kafka probably knows this. Running a distributed system like Kafka is not easy because you have to set up the configuration, you have to worry about monitoring, logging, upgrading, and then expansion. So this can be cumbersome, especially if this is not your core business. By offering the software as a service in the cloud, Confluent now becomes the operator of the system. This allows our users to focus on their core business. Next, I'll just provide one example how this cloud offering helped the business. The example I want to share with you is about a cloud-native retail bank. This bank is unique in the sense it doesn't have any physical branches. The whole company only exists in the cloud and is accessible through those mobile applications. The whole bank was able to be built in 300 days, and a big part of the reason is they have been leveraging those cloud SaaS infrastructures, such as Kafka and MongoDB. With the usage of Confluent Cloud and MongoDB in the cloud, they build 60+ microservices on top of this platform. All those microservices are event-driven, and they are constantly listening to the changes that's happening to their user. From there, they can derive better insights for the user, and then guide the user how they have been spending their money and how they have been investing their money. So what's the end result for that? Well, for them, even though the bank is relatively young, but for some of the offerings they have, they are considered the best in their category. So this is just one example how using those cloud infrastructure services can help a business innovate fast. But taking Kafka and putting it in the cloud is really just the first step. If you look at all those successful cloud SaaS companies dealing with infrastructure, they have all been implementing that infrastructure in a cloud-native way. The cloud environment is fundamentally different from on-prem. In the on-prem world, you will buy some hardware, and then you can sort of use that for free forever. In the cloud, it's different because you are typically charged by how much you are using those cloud resources. By rethinking about how software should run in the cloud, those cloud-native implementation can use the cloud resources much better, in a much more efficient way, and therefore deliver a much better service. Next, I'll just talk about one specific example how such a cloud-native implementation can benefit Kafka running in the cloud. This is how Kafka stores the data today. We have a cluster of those brokers, and each of the brokers has some local storage. So for all the data assigned to a broker, they are all stored locally in those locally attached storage. Now, what's the issue of running this architecture in the cloud? Well, the first potential issue is in terms of cost. In Kafka, we have 2 types of data. One is the more recent real-time data. The other is the older historical data. The most recent historical data typically need to be delivered in real time, and they really care about low latency. But for the vast majority of the historical data, they don't necessarily need to be delivered with low latency. So if you only have one type of storage that you can choose locally, then you have to choose those fast and potentially expensive storage to deliver those low latency requirements for the real-time data. But what that means is you're potentially overpaying your storage for those vast majority of the historical data. That's the first potential issue. The second issue is in terms of elasticity. Since the local storage is really tightly coupled with the broker, now you can't really scale the cluster independently based on the compute versus the storage needs. Since the local storage capacity typically is limited, if you need more storage capacity, often what you have to do is to add more brokers. That just means that you are unnecessarily using and paying those unused computing resources. What we did in Confluent Cloud is we rethought a little bit how Kafka should store the data in the cloud. And in particular, we introduced tiered way of storing the data. So for those real-time, small amount real-time of data, we continue to store that in those local fast type of storage. But for the vast majority of historical data, we can choose to archive them into external remote object store. And we only need to keep the references of those data locally in each of those brokers. Now, what does this new architecture help with Kafka running in the cloud? Well, it actually helped a lot. The first thing that helped is in terms of cost. By storing the vast majority of the historical data into the external object store, we can leverage those potentially cheaper object storage to offer a much compelling overall storage cost. The second thing is it also helped with elasticity. Since now the vast majority of the data in the broker is decoupled with the processing of the broker itself, we can now scale the storage independently of the compute. If you do need to scale the broker in terms of computation, now adding a new broker will be a lot faster because we only need to move the small amount of real-time data that's stored in the local storage. That's going to be much faster, and that's also going to be much more efficient in terms of the resource usage. Last but not least, by truly rethink about how Kafka should store the data, we are now offering a new capability, which is we can now truly store the data infinitely in Kafka. Now, why does this matter? Well, to me, I think this opens up the opportunity of unifying the data at rest system versus the data in motion system. Traditionally, most people have this impression that for data at rest, you can keep it for long or forever. But for data in motion, since it's really designed for real time, you don't keep the data there for long. But for a lot of applications, sometimes they need to access both the real-time data and occasionally also the historical data. So now what do you do with those applications? One solution is for those applications to interact with two separate systems, one for data at rest and one for data in motion. But that just adds the administrative complexity. With the infinite storage capability in data in motion, now we can truly unify these two systems. By storing the data infinitely in Kafka, now you can truly power those applications with just a single platform. Next, I will just share with you a real use case how people are leveraging this new capability. The story I want to share with you is about a large US custodian bank. This company is leveraging this infinite storage capability in Kafka to build their system of records. What they did is to extract all their core events, ranging from ledgers, marketing information, all the information they collected from their investors and customers into Kafka. And within the Kafka, they are keeping the data for as long as we need for various applications. And all the data in Kafka now becomes a single source of truth for all their downstream applications. From there, they build a bunch of event-driven microservices that can provide ability to do real-time alerting, real-time reporting, and real-time deriving insights of this platform. Occasionally, they need to create a new instance of those applications to scale. But what they need is to be able to bootstrap the initial state for those new instances of applications. By keeping the data for those applications in Kafka for weeks, they allow those applications to be bootstrapped within the same platform. They are also opening this platform for their third-party vendors. When they try to onboard a new third-party application, they want to provide a look-back window for those applications. By keeping the data in Kafka for months, they allow those applications to be bootstrapped from the look-back window, again, using a single platform. Sometimes this bank have some batch processing needs. They may need to do some batch reconciliation. They may also need to do some auditing for some historical data. By keeping all those type of data in Kafka for years, they allow the same platform to be leveraged for those batch-style reconciliation and auditing purpose. So that's an example how by providing this infinite storage capability in this platform, we are allowing this platform to be truly used as a single source of truth for various applications that needs to access both real-time as well as historical data. Providing this cloud-native storage is just one example of the cloud-native implementation. At Confluent Cloud, we have many other types of innovation where we have rethought about how we should deploy Kafka more efficiently for multi-tenancy, for more efficient computation, and for geographically distributed environments. Some of the more recent innovations are we recently announced general availability of a technology called cluster linking, which provides this capability for providing high availability in those geographically different environments. We are also announcing the general availability of this infinite storage capability in GCP. By the way, we are also taking some of the cloud-native initiatives into Apache Kafka. In Apache Kafka, we are adding the tier storage capability I mentioned earlier through KIP 4.5. To conclude, we are at an exciting time for digital transformation. In the last few years, we have witnessed the strong adoption of this technology based on data in motion, which allows enterprises to have this deeper level of leverage of this data. In the last few years, we have also witnessed the adoption of the cloud. Going forward, I think the combination of data in motion and cloud is going to play an important role in the future digital transformation. By offering data in motion as a cloud service, we are significantly reducing the effort of our users to adopt this technology. By providing cloud-native implementation of data in motion in the cloud, we not only are providing a compelling and efficient service in the cloud, but we are also opening up the opportunity for this platform to be used as a single source of truth for both real-time data as well as the historical data. I can't wait to see what's happened next. With that, thanks for listening and enjoy the rest of the conference.